Okay, so looking at your problems for today, the first one I want to look at is the one with the graph. I want y'all to look at this with me while I read off of the traces, because I don't think I have one here. Anyway, do this with Grace and I. It says y equals what at the very tippy top of that? Okay, circle that. Okay, circle that.
I found it.
The figure, okay, the figure, then follow along. Note, underline. This is the graph of the derivative, underline that. Circle that. Not the graph of f. Then they start the problem. The figure above shows the graph of f prime, the derivative. They told you 4 times. They are not trying to trick you. They are yelling at you. You are looking at the derivative. You are not looking at the function. It's not like they said it one time. So do y'all see how they like, hello, you're looking at the derivative, all right? So, and I would say that some of you that I talked to you about this in the last couple of days would verify that it can trick our brains to look at something going up and down as opposed to what it is, not what it's doing, okay? So when I looked at the derivative, and it's going like this, something like that, okay? I know that this is derivative. They told me 4 times in the space of a small amount of time. I know I'm looking at the derivative, but I know that I'm going to be tempted to call these horizontal tangents, okay? Those would be the horizontal tangents of the derivative. Those would be something we call later on points of inflection. I don't care about that right now, okay? Your brain, get away from that, all right? So do a plus minus chart, not as verification or justification, but this is like notes to self. And I'm not going to look at that anymore. I'm going to get away from that as fast as I can. And I can't preach that enough, because sometimes they'll say, hello, this is the second derivative, and ask you to go back to the original functions. You got to really know the literal process behind it, okay? Just make it as literal as you can. This literally, what it is, remember that big conversation we had the other day? I'm looking at what the derivative is. If it is positive, my original function is increasing, and so on. My derivative is 0 right here, right here, right here, and right here, okay? Notice that I put my limits here. They told me this is only from -10 to 10, I believe. And it's a good idea to put that on your chart, because you can't really say something's increasing from something to infinity if you don't know what's out there. So I might say increasing or decreasing from 7 to 10 or something. This graph only exists from -10 to 10. I'm just kind of going from memory here.
Yeah.
What are these zeros? I don't remember. -7?
-1, 4, and 8.
Okay, so this, and then it's negative is negative, positive, negative, positive, negative, okay? And again, it alternates. Don't get all caught up in that. There's lots of things that don't alternate. We'll see them. So don't take that for granted. So this is negative, positive, negative, positive, negative. What is really happening here, Carolyn and I were talking about, like at -3, I get 3. That means the derivative is 3 at that moment. The derivative is not 0. The derivative is 3 at that moment. So this way up here in the positives tells me at that moment it's increasing pretty rapidly. Do you see how your brain can fool you though? So I'm going to bank on this right here. I'm going to make note to self about my original. My original is decreasing, increasing, decreasing, increasing, decreasing. So this is a kind of a lackadaisical, super rough sketch of what my original is actually doing. Now, I can't just leave that there for justification, but these are all notes to self, and I would do everything off of this instead of off of this, okay? And it makes it just clear cut. It makes it really nice. Instead of you having to go, wait, now my brain's confused. So you've laid it all out, and I'm looking at this. On the A part, I would say it has a horizontal tangent when x is -7, -1, 4, and 8, because I don't care if they said justify your answer or not. At the beginning of the free response in all caps, it says show all work. Because f prime of x is equal to 0. Okay, so you've told them why. You know, because your derivative is 0, those are horizontal tangents, okay? Will somebody read me the A part? I want to talk about the way I answered that question. Emily, you want to, since you found your sheet?
Yeah. For what values of x does the graph of f have a horizontal tangent?
If they asked Emma for what values, they would want the y, okay? But they say what values of x, or what is the x coordinate. So I don't even know the y's. You may wonder how I can find the y's. We can find them later. Right now we're not ready to do that, but I can actually find the y values, which is remarkable. But anyway, I was reading, gosh, what a nerd. I was on Facebook this morning before school at my apartment, but I was just looking at the AP Calculus Readers page because it's so exciting to me. And there was this big discussion about a newer teacher was asking, it's a great resource really. You know, a newer teacher was asking, what if they give the point when all they ask for is the x coordinate? Or what if they say, what is the maximum value, and they give the whole point? I'll be coaching you through all of that, but only give them what they ask for. You can lose the point by giving them something they didn't want, okay? I'm using the point in the English language 2 or 3 different ways there. But suppose I knew that the derivative was 0 at the point -7 comma something. They didn't ask me that. What's the x value? Sometimes you'll be kind of scared to not give the point, the whole entire thing. So there's ways to answer their question. You can say, when x is 3, the maximum value is 7. You know, and then, but I'll coach you through all of that. But make sure you answer the question, only the question that's asked of you. Okay, the B part. It was really interesting to walk around the room and see how short and concise this problem was. You got all that room to work, you didn't really need it. However, if you don't know calculus, there's no way you can answer this question, is there? You gotta really know a lot of calculus to give that nice little easy answer where you have horizontal tangents. You've got to know where your derivative is 0. It's really nice to know you will face questions like this on the free response. Okay, then the next question is, for what values of x on the interval from -10 to 10, notice it's an open interval. You don't have to consider the endpoints, okay? Does it have a relative maximum? All right, so my relative maximums occur right here at -1 and an 8. We're the only two?
Yeah.
At x equals -1 and x equals 8, and I would say because f prime of x equals 0 and changed from positive to negative at these x values. So make sure you're very clear. I might even reiterate, because my derivative is 0 and because f prime changed. One thing you have to establish is why you're even looking at it, okay? Your derivative was 0, so it maxed out, and it changed from, your derivative changed from positive to negative, okay, Caroline?
What would you do if you still don't have y values, but they ask you an absolute
Max or min, you wouldn't know yet.
So you'd have to have the y values, right?
In fact, one of those has to be the absolute max.
But you don't know until you have the y values.
Does anybody want to guess which one's the absolute max?
Negative.
We'll do it later, but it has to do with displacement.
Okay.
We can tell by that graph and the derivatives how far, like, we can put all of that together. Okay. But you'll know how to do that later. Right now, you have no idea how to find those y values. If you don't have the original function, you don't know. Emma?
For the second part of, like, when you're explaining it, you don't have to put any, like, values or anything, right?
Yeah,
like,
that's
when you, like, you can just say it changes from positive to negative, and that's fine.
Yeah.
Okay.
So let's pull up the grading standards for that if I can. Did I give you the year?
Yeah, 1999.
Way back in 1989?
Yes.
Okay, in the 1900s. Okay. 1989 AP Calculus.
It's the AP.
Let's hopefully, what I'm looking for right now is the grading standards from the College Board. Oh, here we go. What number was it?
5.
Isn't that refreshing to realize that's number 5 on that year's exam? Okay, not that you can really tell what order things go in. I think you've seen one similar to this. It was sort of like the sign one I gave you a while back.
Yeah. Same.
Let's see. All right, here it is. So here's what they want to see. This is what I would be looking at as an AP reader. Horizontal tangent occurs when the derivative is 0 at those points. You have relative maximums at x equals -1 and 8 because f prime changes from positive to negative at these points. So. And then concavity is very succinct, like do you know your calculus or not? Okay. I'll teach you concavity later. I'm tempted to do it now, but we'll do it later. That's why, at least for once, I'll remember to eliminate C, whereas lots of times I'll leave that out there and you don't know how to do it yet. Did I say eliminate C?
Yeah.
Okay. Now let's go to the crazy JT building. That's a crazy problem. I usually give that problem in a somewhat safe environment, like as group work or
Safe environment.
yeah. That problem, I'm just like, I don't even know what you're talking about. Like, I would have to actually do what I was doing with people. And the math center, like, notice where,
Yeah, I can't figure out where my shadow.
here we go. The problem is, you've got to imagine a Broadway play or a circus or something where, I just went to the circus, that's why I keep saying circus. But they have the spotlight that everything's dark. And you know, if you have a tightrope walker, really, I actually saw this in motion the other day at the Big Apple Circus. But if you have a tightrope walker with the light source and they make everything else dark, you see their shadow moving on the ground. Y'all see that's what's happening. What's hard is that we live around so much light. But if you're in Central Park and you just get in front of a lamp at nighttime, you can actually watch your shadows shrink and grow as you walk toward the lamp, away from the lamp, and so on. And it's proportional. Okay. Now what happened at the end is as you get closer to the wall, you see the shadow starting to come up the wall because I can't go out. My shadow is not like Peter Pan and go outside the door. Okay. So my shadows, if I had a light source behind me, my shadow would be in front of me. And as I walk, eventually it's going to start to come up this wall. Can y'all see what I mean?
Yeah.
Okay. And the closer I get to the wall, is once it reaches the edge, it's going to start to go up. If you, again, can kind of imagine Peter Pan, I think there's a scene in that where that actually happens. So there's this J&T building, the tightrope walker. I didn't draw it to scale because I think the light source is 70, and this was 30. Okay, and this was 50. Those are set in stone. But the girl, the tightrope walker, is walking. Okay, so that I can never put in as a constant. She's in motion. As the light source hits her, do y'all see that it throws a shadow on the ground? Okay, so her shadow is going to be like this, moving across as she moves. So the A part, I said X. I think I called it different variables with different people. So let me do what I did this morning. I think I called that X and Y. Just label it however you want to. I'm going to stick with these right now. So I'm going to set up a ratio, and I'm going to say Y is to 70 as X, not as to 30, but as X is to what? 100. You might want to do a little bit of algebra just to make your derivative easier. And so I'm going to say 100Y equals 70X. Then I have 100 dy dt. Do you see how now that you have a little bit more calculus maturity with a few weeks under your belt, how similar this is to implicit differentiation? Why I teach that first. After every variable, you stop and say something except for t. Okay? So they told us how fast the girl was walking, which was 2 feet per second. Okay? So then I put that in, 100 dy dt equals 70 dx dt. So then dy dt is 140 over 100. Did I mess this up again? I feel like I messed it up this morning.
Hold on, let me check.
It's not, the 70 isn't times 2, it's the 100 times 2.
So, okay, there, I did that exact same thing this morning. I think it's because the first time I worked the problem, I actually labeled this X. dy dt is how fast she is. Thank you, Caitlin. I would have never figured out what I was doing wrong again, even though I just did a little while ago. Do y'all see I've got to be really clear? I'm calling that dy dt, so that's how fast she's walking. And so this is dx dt, and this is 2. All right, so you get 200 over 70, which on a free response you can leave. Sometime as the year wears on, I will share with you some hysterical things that we actually graded. Like what I mean is you've taken this long derivative and they say, what's the derivative at, 4 comma sine of 80 or something. And a kid has taken the first derivative and left it in its purest form under all these square roots and denominators, and they actually just filled in the point we gave them. They didn't even clean it up, or don't clean up part of it. I mean, you had to like really plow through someone's work to see if they left it correctly and if they did simplify it, you get complete full credit. So it's a very safe thing to do. We sort of wanted to give those a gold star, other than they were harder to grade. I'll show you some. So anyway, you can leave it like that. Most of y'all probably reduced it to 27ths. You might not get any credit for this if you didn't say feet per second. Always get the units, okay? And unfortunately for me, if they have the grading standard, this was 2 points out of 9, and 1 point was for the setup, and 1 point was the answer with units. I can't give the second point if you don't write units, okay? Here's your drive to do it, even if you certainly believe me, I always want to put units anyway. Because there's been so many disasters in the real world. Your algebra teacher probably shared those with you. There was like a whole entire, millions if not billions of dollar space shuttle that they lost because someone handed it to them in English and they thought it was in metric, and it's gone. Like down our taxpayer money's like, thank goodness a person wasn't on it. But there's lots of disasters where somebody thinks you're talking in one language and you're talking in another, whether it's dollars and cents or metric in English or whatever. So you want to give your units of measurement as a good person. Another reason is sometimes we give credit if you have the right units of measurement. Sometimes I'll grade something as a reader for 8 points. And at the bottom of my sheet it says to give them a point if they use the correct units of measurement. So sometimes they miss the problem, they can still earn a point because they got the correct units in there. I don't know how to make these decisions, but anyway. Let's go to B. B was curious because it was like an Algebra 1 problem. And you may wonder why they put it in there, and I'll tell you why. It said, how far from point A is a tightrope walker when the shadow of her feet reaches the base of the T building? So at some point, her feet she's gonna walk far enough somewhere to where her shadow is gonna hit the base of that building. Okay, we don't know where it is, so we're gonna find out. So I'm gonna put on the B part, y is to 70, as x is to 100. I'm doing something wrong. Okay, I wanna do y is to 70. Oh, you do know x there, it's at the base of the building. So yeah. X is gonna be 50 to 100. So you know that for sure. So it was just a straight up ratio, 50 to 100. All right, so that gives me y is to 70 as a 1 to 2 ratio. So y ends up being 35 feet. Okay, which is interesting. What they're trying to get you to do, why they threw B in before they asked you C. And whether you realize it or not, y'all see 2 reasons I'm going over these problems, because so many of you went over it with me and you're seeing the same old thing again. Hopefully it's just reiterating or making you stronger. Both problems, I'm showing you a lot of information they give you to help you. It took you 4 times you're looking at the derivative. You are not looking at the original. Here, they didn't have to put B in. They could just say C about her shadow climbing up the wall, and you would have, even though all of us probably stopped at C and went, huh? At least they've set the stage for she's not all the way across, but her shadow has hit the base of the building. So where's the shadow going to go? It's going to start climbing up the wall, okay? So that's why they gave you that one, 35 feet. So then the C part is, how fast is the shadow of the tightrope walker's feet moving up the wall when she's 10 feet from point B? Girls, you can't put 10 yet. Is she going to stay out there forever 10 feet away from the wall? If it's moving, you can't put it in the original. Okay, so you can't put in 10s and 40s yet. But you see, you just learned, they forced you to learn that at 35 feet, it hit here. So what happens when she's 40 feet? It's got to be climbing up like this. Okay? So that created this scenario. And y'all see these similar triangles right here and right here? Okay? Now, she's not going to always be 40 feet from here and 10 feet from there. So if I stick with calling what she's going across y, then what is this left over right here? 50 minus y. And you could have called it x, but it's two things. I don't want to call it x because I already called something x in my problem. Another thing is tie things together as much as you can. Like if this is 40, isn't this 10? If this is 35, then that was 15 and so on. So it's y and 50 minus y. I called this h this morning with people I was working with. But you could use whatever variable. Okay, so now, unless they tell you to. Sometimes they tell you to use a certain variable. So on C, I'm going to say h because this is changing as it starts to climb up the wall. Do y'all see what I mean? That's h over 50. That's a really cute little h. H to 50 minus y as y is to 70. You could take derivatives there, but you might want to do a little algebra beforehand, which is another reason I'm doing this problem with you. So I'm going to cross multiply and say 70h is equal to 50y minus y squared. I didn't do it this way. Did I have my ratio set up right again? Hang on. H is to the base. I have them backwards again, don't I? All right, so I should have this side right here to the base, and here I should have this side to the base. I need to be consistent. Sorry, y'all should have caught that. Do y'all see what I mean as far as my similar triangles from geometry? Sorry about that. Okay, now, I don't have to set it up that way though. I showed some people this morning that you also could do this. You could go side is to side as base is to base. So I could say h is to 70 as 50 minus y is to y. Couldn't I go side is to side as base is to base? Okay. So watch what happened if I did that. I could go h is to 70 because it's proportional. H is to 70. And go back to that same triangle, the small one, 50 minus y is to y. And then I have 1 over 70h is equal to 50y to the negative 1 minus 1. All right, so this is a coefficient 1/70th. This is 50 divided by y and y divided by y. And then I have a really easy derivative to take. Okay, so it's just something to think about. Up here, if I had worked with this one, do you see I would have had a quotient or a product rule? I'd have to handle dh dt and dy dt embedded in the problem. So you might want to rearrange it a bit and give yourself the easiest derivative to take. Are y'all with me so far? All right, so then I'm going to say 1 over 70 dh dt equals negative 50 y to the negative 2 dy dt. And it's a lot easier derivative than some of the other ones I've taken on this problem. All right, now you've got to make sure you put the correct y in. How did y'all tell me to scroll up? What?
Go to full screen.
Okay. Now where's my...
Scroll down. Command minus.
Oh well, okay, so anyway, over here, I don't know, have any rhyme or reason as to why that does that. That's 1 over 70 dh dt is equal to 50 over y. You gotta be sure you grab the right y. When she's 10 feet away, in my problem, the way I've labeled it, y would be 40. So you freeze frame it. So if I put in 40 squared, dy dt is 2. If this isn't a calculator active problem, gosh, I wish that would go. All right, if it's not a calculator active problem, I'm just going to erase this so I can keep on this slide. Okay, so if it's not a calculator active problem, or this is good standardized test taking skill, which most of you may be through with them for a while, but this is 1/70 dH dt. This is 500 over 1600 times 2. And so I can reduce that, and 2 goes into 16 8 times. So I have dy dt, dH dt, I'm sorry, dH dt, that gives me, why do I still have a 70? Oh, because I got carried away with did my 50 turn into a 500? Isn't that just 50?
Yeah.
That was just 50. Sorry, it was 50, let me go back. I'm just in a hurry to go to something else. I'm being careless, I'm sorry. I'm in a hurry, I want to tell you this stuff, but I want to move on. All right, so that was a 50 over y to the negative, 50 over y squared dy dt. So this is 50. Okay? So now I'm going to erase this part and keep going this way. All right, so I have dH dt is equal to, I'm going to multiply 70 times 50 times 2 over 1600. I'm not going to multiply all that out. Even if I did have a calculator, I can just reduce like this. And so you get 35 over 8 feet per second. Oh, by the way, I lost something also in the process of being in a big hurry. It was negative 50, y to the negative 2. So let me go back. This is real important. So right here, when I bring this down, that should be negative 50. This should have been negative 50. So I get negative 35, and that makes sense because as she walks across, isn't H shrinking? H is getting smaller and smaller, so its rate of growth is should be a negative. Sorry, I have so many points I want to make that sometimes I don't care about the solution. I want to make the point, but then I know it's distracting when I make mistakes. I'll probably lose the point I was trying to make. But is that okay? All right. One thing I would say for sure is just have tons of confidence. And I would say once your pencil hits the paper and you start playing around with the frustrating problem, you get better and better and stronger and stronger. So, all right. So let me, we may go to this worksheet in a minute, but let me show you the new material. What we're going to talk about today is called the mean value theorem. You can refer to it as the MVT. MVT, and everybody will know what you're talking about. It's obviously similar to the IVT. Later on, we'll have the average value theorem. Remember, the intermediate value theorem based itself on continuity, okay? Because just because I have an f of 1 equals 4 and an f of 5 equals 10, does there have to be some f of c that equals 8? Going back to the intermediate value theorem. When I answered that on a test, that's one of the things that must be true. All right, we got a yes. Sophia, if it's continuous, right? I don't have enough information to say that has to be true. If it's not continuous, I don't have to hit 8. If it's not a continuous function. Because Sophia and I could be at 1, 4, and at 5, 10, and our graph could look like that, couldn't it? Okay, or it could be a piecewise function that jumps. There's so much I don't know about it. If it's continuous, I can't help but get from 4 to 10 going through 8. Are y'all with me there? Remember how I talked about grades? You know, if you made a 75 on a test, and then you made an 85 on a test, then your parents go, oh, well, that means you made an 80 on another test. So that's not continuous. But if it's 75 degrees and then later in the day it's 85 degrees, sometime during the day at least once it had to be 80 degrees. MVT is all about parallel lines. Well, tell me what you know about parallel lines. Same slope. Okay, MVT, the very first thing and last thing you need to know about it always is parallel lines. In fact, if you see the word parallel, they're probably talking MVT. And moving as fast as I do, I think I told you in one little snippet in an email one time that normal means perpendicular. Some of you in physics know the normal force is the one acting against another force in a perpendicular fashion. It's very important. So if you see the word normal, you're talking about a perpendicular slope to the tangent line, okay? So what would happen there is you would have something like this, a tangent line, and its normal force would be like that. The important thing is all three of those share that one point. That's about normal. Back to MVT, all right? So back to MVT. MVT is all about parallelness. It's all about the wonderful instantaneous slope, and it's remarkable and wonderful and fabulous and awesome, and then there's the crummy slope. This one's amazing because you can go, hey, what's happening over there, and where are you? You're up in the middle of it, right? You're like, I was there. It happened to me. The crummy slope, I use it as a Miss Lazari term. Please don't use that anywhere else on your test or even in my room. You gotta say the right thing. What slope have you been finding when you found the difference between 2 points?
Average.
The average slope. Who wants that? Okay. I don't want to be average. Okay. So, but what happens is sometimes the average crummy slope can equal the instant slope. Okay? So you know that old crummy slope that you found, which up until calculus you found it a lot. You would go, well, I was here and now I'm here. And so my rate of change was y minus y over x minus x. And it probably wasn't. Maybe not at all. You see how misleading that can be. In a situation like this, that's the slope. That may have been what happened. So it can be very misleading. However, suppose that I wondered if when you were driving, if you ever went 60 miles an hour, okay? If I know for sure that you were clocked at 35 miles an hour, and then later on you were clocked at 70 miles an hour, I don't think you can deny that at some point your speedometer went through 60 miles an hour. Do you see now I'm not talking about points, I'm talking about rates, I'm talking about how fast you went. Now, if your average speed was 60 miles an hour on a trip, okay? If your average speed was 60 miles an hour on a trip, we say that a lot. Like for instance, if I'm gonna drive somewhere and I wanna get there in 3 hours, like when I would go drive from Memphis to Nashville, and I would think, God, to get there in 3 hours is 210 miles, I gotta drive 70 miles an hour. So I get in my Jeep in the parking lot of the school I used to work at, and I peel out of the parking lot at 70 miles an hour. No, I must be going like 80 interstate for a while. Right, y'all see what I mean? And I'll probably stop and got a cup of coffee at Starbucks knowing me, and Jackson, Tennessee, and the little stop there.
So you were like 170 miles.
So y'all see how that's an average rate of change, okay? But once I got there, here's the deal. Like if you were trying to fool your parents and they didn't want you to drive fast, and you got somewhere in 2 hours, it should have taken you 3 hours. You should wait an hour and call them and say, okay, now I'm here. Because if you call them after 2 hours, they're going to calculate how fast you were driving in a hurry. And you couldn't argue them down, even if they know your average rate of change. At some point, if you got there and you want to argue down that you never drove 80 miles an hour, they'll know that at some point you did, right? You probably went faster than that. So that's only if something is continuous and differential. Y'all see now I'm talking about a rate? Okay, so here's the average rate of change. That's the difference quotient. But right here, somebody was going really fast. However, at some point during that time, they are going that speed. At some point, they've got to hit that crummy slope, only if it's continuous and differentiable. Do you see it's got 2 words on it now? Because if I had this, what's the rate of change from here to here? 0. Is this person ever going to hit a slope of 0 throughout this time? The slope here is probably 2, and what's the slope here? -2, but is that differentiable on that domain? Do y'all see it's not differentiable? If it's not differentiable, I don't even care if it might happen. It's game over. It's just like if it's not continuous, you and I are going to keep working the problem with the IVT. With the MVT, if it's not continuous and differentiable, just don't work the problem. You can stop. You can go, it does not apply. So your homework problems will be like that. Okay, so let's look at this awesome animation here.
We have a definition.
Yes, here we go. So oh, I know where it is. It's here. Let's look at this. Here you go. If f is continuous on the closed interval, it has to be continuous even if it's in points. Continuous on the closed interval and differentiable on the open interval, then there is some number between a and b such that the instant derivative equals, such that the instant rate of change equals the crummy rate of change. Did y'all see I started you out today, so you don't have to memorize a whole lot. It's all about parallel. Did y'all see those are same slopes? What is f prime over g? That's the slope at an instant, and this is the slope over time. This is also in your book, on page something, right before your homework's done. Let f be continuous on a closed interval. Okay, so here's what you need to know. The mean value theorem is all about something's parallel. If it's continuous and differentiable, the instant slope somewhere has got to be the same as the crummy slope. I'm going to show you, this is awesome. All right, did y'all see the average rate of change between A and B?
Yeah.
Did y'all see the crummy slope?
Yeah.
At some point, there is a point P to where you actually have that slope. Do you see they're parallel? All right, now let me change the slope. Did y'all see what's happening? Watch this.
Wow.
All of a sudden, there can be 2 times where that happens. The great animation. But as I move this crummy rate of change, what I mean by that is not all, that dotted line, it doesn't tell me the slope of that green line, that green curve. However, once I lock in on that, if it's continuous and differentiable without any discontinuity or any corners and pointy points, I definitely will at least achieve that slope somewhere in there. Okay?
Can you scroll up a little bit?
Yeah, just for a second.
Yeah.
It's in your book. And I may have provided you this link, I don't remember.
Okay.
All right, so remember the animation, you can look back at it, I'll try to remember. I didn't provide the link.
No, it's on the, isn't it on the, like, what do you call it? The schedule?
It's on the syllabus, yeah. I bet it's in there.
That's great.
Let's see, I'm not super good at updating that syllabus, so that's like one of the things I'm worst at. But I think it was in there. Maybe not on the right day, but it's in there somewhere. Is it? I don't see it. I give up. Okay, anyway. Let's do a problem before we go on mean value theorem. All right, so will you hand me the book, Caitlin? Please.
What is it? It's one of the baby dolls.
Let me show you all of the pictures. These are so cute. We'll have to have these slides again. This is my favorite. Isn't that sweet?
She loves that picture.
Isn't that sweet?
Yeah, she does.
A little Halloween pin. Okay. But we'll have them again. That's adorable. All right, the mean value theorem is on page. It's kind of not. Oh, here it is. It's actually in 3.2, and we've kind of gone into 3.3 already. But it's in chapter 3, section 2. All right, so I'm going to do an example. Okay, so let's say if I have f of x is equal to x squared minus 5x plus 4 from 1 to 4. Okay? So this question says, it really says something else I haven't told you, so I'm going to pretend like it says it's about the mean value theorem. The mean value theorem is like, show us that there's some number c between 1 and 4 to where the slopes are the same. Okay? Let me read the wording to you to wherever you for instance, determine whether the mean value theorem can be applied on the closed interval. If the mean value theorem can be applied, find all values of c such that f prime of c equals f of b minus f of a. All right, before we go on, do y'all understand that's what parallel is talking about? F prime of c is f of b minus f of a over b minus a. Is that same slopes. Crummy average slope equals the instant slope. That can only happen if it's continuous on the closed interval, differentiable on the open interval, and there's reasons for that. All right, would I go forward with this problem on the MVT? Is it continuous on that interval? Then take the derivative, you're going to need it anyway. So the derivative of that is 2x minus 5. Is that differentiable on that interval? So the derivative does exist. Like I said, you needed it anyway. So now let's find the slope. Let's find the crummy slope. So I'm going to find f of 1 and f of 4. So f of 1 is 0. Are y'all okay with that? 1 minus 5 plus 4. And what is f of 4, girls? Somebody's already found it. It is 0. Okay? And so now when I find the slope, when I go y minus y over x minus x, my slope is 0. And that must equal, the derivative must equal 0 sometime in between them. So you see I find the slope and the derivative and I set them equal to each other. That's what I do. I find the crummy slope and the instant slope and I set them equal to each other. So now I'm going to take out f prime of c and put in, I'm just going to put in 2x minus 5. I'm going to go in and use x. So I'm setting my slopes equal to each other, 2x minus 5. So I have 0 equals 2x minus 5. And so 5 is equal to 2x. And so x is equal to 2.5 or 5 halves. So what should I see happen at 5 halves? I even will have a kind of the tricky thing, like accidentally I even found a critical number, didn't I? Okay, because I happen to be looking for a horizontal tangent. All right, so if you graph this, x squared, the vertex must be right here. Do y'all see what I mean? Okay. And so what would happen is if you filled in 1, you got 0, and if you filled in 4, you got 0, and it did that. Now let me go back to the animation for a minute. Where is it? Oh, here it is. All right, watch this. It's not letting me do it. Do y'all know what I'm trying to do?
Yeah, I get it. Like,
Trying to get them what? About got it. There we go. Just like what Emma did, okay? If I get the points level, then not only am I finding the derivative that equals the slope, I'm actually finding the derivative that equals 0, so I accidentally found critical numbers. This is where I wish my name was R-O-L-L-E, so I could be whatever, I think it's John Roll, I don't know his first name, it's probably not John, his name's too easy for a mathematician. But it's actually, I just taught you Roll's theorem. Roll came along, and it's like a corollary to the mean value theorem. And I want to go, I mean, most of it just roll our eyes at Roll. Like, okay, whatever. I mean, he's like, oh, but wait, you know, here's the mean value theorem, and they're parallel, but what if the endpoints are the same? Then you found a critical number. And I just want to go, duh. I mean, it's not fair that he gets his name in a book for that. Y'all see what I mean?
Yeah.
So, in fact, the AP program, I don't know if I've ever seen them use the word rolls, because you see that will just happen naturally with mean value. In your homework, though, when you see rolls, what will happen is the endpoints should give you the same number. Okay? In fact, they even say the endpoints have to give you 0. They don't have to be 0, they just have to be 5 and 5, so that when they subtract, the slope will be 0. Y'all see what I mean? All right, let me work another kind of sketchy problem here, and then we'll go. So, suppose I have f of x is equal to the square root of x minus 2, and I'm on the interval from 2 to 5. And the question is all this mean value theorem stuff that you'll see in your homework. You don't have any problems, by the way. And some of them you don't even have to do, because if I had this, f of x is equal to 1 over the square root of x minus 2, I would get to say in my homework the mean value theorem doesn't apply. Next, okay? I mean, because is that continuous from 2 to 5 inclusive on the closed interval? Y'all see what I mean? Yeah. Over here, is this continuous from 2 to 5? Yes, because you can have the square root of 0. So that means right now I go forward. Now I'm going to check for differentiability, which I got to do anyway if I'm going to work the problem, right? So you're going to see if it's differentiable, but you're going to need the derivative if you're going to keep going. So my derivative, to go fast, is 1/2 x minus 2 to the negative 1/2 comes 1 using the chain rule. So my derivative is 1 over 2 square root of x minus 2. Now, does my derivative exist on the open interval? There's a little bit of grace and forgiveness in this theorem. It's like it doesn't have to be defined at that endpoint. So do you see that it is defined on the open interval? I didn't want to let class go without showing you one of these. So they're just saying it's got to be continuous on the closed and differentiable on the open interval. Okay? All right, now, that means I'm going to go forward, and I have my instant slope. What am I going to set that equal to? This is my wonderful, awesome, Superman slope. I'm going to set it equal to my crummy slope. How am I going to find my crummy slope? I'm going to fill in these numbers, all right? If those numbers happen to be the same thing, I'm accidentally doing Roll's theorem, okay? But I call it all the MVT. So f of 5, I believe, is square root of 3, okay? And f of 2 is 0. So I have the point 5, square root of 3, and 2, 0. So I'm going to say y minus y over x minus x. So I have 1 over 2 square root of x minus 2 equals root 3 over 3. Oh, and I can't expand it. So I have 3 equals 2 root 3 times the square root of x minus 2. Sorry, I'm writing in yellow. So I'm going to say 3 over 2 root 3 equals the square root of x minus 2, and I'm going to square both sides. So it gives me x minus 2 equals 9 over 12, I believe. Does that look right?
Yeah.
And what is that?
3/4.
3/4. So 2 3/4. So what happens if 2 3/4 is this? The square root of x minus 2 looks like this. You found the slope from 2 to 5, and it's telling you at 2 3/4, you actually have the same thing. One other thing I wanted to show you, your animation showed you, do you see as it moves like this, the slope is changing, and if it's differentiable at some moment, by the way, I just said if it's differentiable, it has to be differentiable, but if I say it's differentiable,
It's good to get.
bye. Homework's already been posted. Keep bringing this sheet with you, don't lose it.